have a reason to use up something.
All right, you ready? Well, since we just got a group, I'm gonna sit here and talk. That's fine, I'm loud. Okay, go on to the first slide there. Okay, so we, talked obviously a lot about geologic carbon sequestration last night. Like I said last night, geology is kind of an abstract thing. So I added some slides in here that show you a little bit more about what this might look like underground, based on theory and practice from experiments. But also, I guess I just wanted to start with this kind of group, and I said it last night, is really important for kind of fact finding and discussion. So I really appreciate it. And actually, the questions both on the poster, I photographed those, and from the questions that I took last night will be the kind of information we'll go and update our webpage with, like frequently asked questions or additional information. So these are, I just want to say it's really good environment to get that kind of information. And as I also said, this is kind of something new for Oregon that we're trying to get our head around. Not just the geology. I think we know a lot about the scientific parts of it, but there is a lot of funding coming to this. And so we have to address those issues head on. So with that being said, when we looked at this last night, in basic principle, this is a cartoon of what geology might look like underground in certain parts of the country, not here, but it's a model from where you have production of coal or natural gas fired plants, and then the piping system that takes that carbon dioxide, moves it to a location of good geologic site conditions where it could be injected, that was the term we used last night, injected underground into a sealed reservoir and stored for a long time. Let's put it that way. Indefinitely, that's a better word. Use words I can say. Okay, go on to the next slide, please. Or actually, go back just 1 second. So the thing we didn't talk about last night, but obviously people have covered, and I also appreciated, was these different types of terrestrial carbon sequestration. I mean, we've gone through a lot of the different posters, elegantly outlined those different techniques. So that's one. We didn't touch on last night, though, that one of the biggest sinks of carbon is our oceans. And so there's natural systems that have operated for millions, if not billions of years to mitigate the carbon cycle within the Earth's history. But it can also, there are ways to accomplish that actually by putting into the deep ocean additional carbon dioxide as well. So that is another avenue of research. We're not going to talk about that, but I did want to at least bring it up so we're fully aware of the entirety of the system. And then geologic carbon sequestration. And so I mentioned last night, those are traditional oil and gas reservoirs that have been extracted. Things can be put back into those. Saline aquifers, so it shows down there in the middle of the diagram, basically saltwater intrusions in old marine rocks. Many of you may not realize they're actually underlying places like the Willamette Valley, where those are marine rocks dating back to 40 million to 45 million years, where the coast was there at that time. There's actually significant issues with saline water in those rocks, ancient salt water, basically from those marine systems, and people have a lot of issues with drilling wells and producing out of them. So those type of, and they'd be referred to as brines, and in my next slide you'll see those. Places like unminable coal seams, things that are not good production type coal, they don't meet specs to use, so those are places potential storage. Shale formations, and then really we're going to focus on basalt or ultramafic rocks is the term there. And basically in general, if you think about a rock, a volcanic or igneous rock, if it has about 50% of it by weight is silica, that's what we're talking about. And I'll talk a little bit further on about these volcanic or geologic formations around here, really defined by their geochemistry, which is their to you and I would be our DNA. And so the simplest way I can explain that in the work that I do is if Whitney is an outcrop along the road over there, and I'm an outcrop, 3 miles away, and superficially in the rock hand sample, they look the same, and we analyze their geochemistry, and we find that you and I are identical, even though we're 3 miles apart. We can begin to make a map of those features and say, well, this was the same lava flow as the Whitney outcrop over there. And so volcanoes, when they erupt, they generated DNA similar to our parents when we were born, have that DNA that reflects them or our ancestry down path. So that's a simplified way to put it, but it's an essential component of this. And so we define rocks by their chemistry, particularly these basalts are about 50 weight. By weight percent of them are a silica dioxide. Okay, next slide. Okay, so I wanted to give you a little idea what this might look like underground. So in the upper left, you see that kind of brown horizon there. That's what we call the seal unit. So this is a rock unit underground that has very low permeability and porosity. And by that, it means that a gas or a fluid does not move very well through that. So by porosity is the open space that would be available to put something into. Permeability refers to how connected are those holes and how well could that gas or fluid move through that. Okay, so a seal unit basically impedes that motion there. So we have to have a seal unit. We also have to have a reservoir of which to store things, and that's kind of that area under the seal unit. And in this case, this is a brine, a saltwater rich area, and so that CO2 plume is injected in there. And basically, from left to right, you see how the pore spaces between individual grains in a sandstone. That's the space that's available to store the gas. In this case, the CO2 is going to create a bicarbonate with that salt water and be stored within those grains. So this is kind of what geologic carbon sequestration would look like in some of these areas in the Midwest or traditional oil and gas plays where they're in sandstone type aquifers and might interact with really deep fluids. And so on the lower left there, you kind of see this is to see how the scale of the operation would look. So that circle at the top in just generic units of 100, that's kind of this bubble of the amount of CO2. And then, yeah, there you go, injected into the subsurface at depths of below 800 meters. So basically more than a kilometer is the target depth for this, of which then the CO2 becomes a supercritical fluid where it's somewhere between a fluid and a gas. And so that's what we want to get it into those spaces. And so moving on to the right, A there, so that's a representation of a layered section of geology, in this case, sandstones, limestones, marine rocks. You see we've gone down more than a kilometer. And then in B, that shows you kind of the differences in a drill core. So that would be roughly 6 inches across and sliced in half. So as the drill goes down, it takes out this core. We can actually see the geology. The light white is the reservoir rock and the brown is the cap rock seal. So if you looked at those microscopically, you'd see the detail where that cap rock doesn't really have spaces for stuff to move through. And then below it, it has open space. And in C and D, that's basically a quartz sandstone, really under a microscopic image. The blue is highlighting the pore space. That is the storage space of where material could go. Okay, and so I wanted to help people visualize what are we talking about. Okay, go on to the next. Yes, absolutely.
Does the brine, so if we're looking at Willamette Valley and they have help the process, or does it hinder the mineralization?
It's different.
Okay.
And I'll get to that in the end. So part of what I've gone to is there were some questions and concerns. So in my last slide, I talked about that a little bit. So let's go to the next. I'll hopefully get back to that. And maybe right here, I can get it to you. Okay, so structural trapping. So how is it trapped in subsurface rock formation? So we talked about you have an impermeable kind of cap rock. And here you see kind of this classic dome kind of structure. This is called an anticline, where rocks have been folded up. And this is classically where oil and gas has come from. And so that creates a seal, a reservoir, and then you have a geometry in the subsurface where you can store stuff. So residual trapping, that's basically where you put a plume into these type of sandstones, and as a supercritical fluid, it moves through the pore spaces in the middle. Yep. And then basically one bubble at a time, it moves and drags the next one, and eventually that gets cut off and it's stored in that pore space, and that's where it stays. It doesn't move anymore. Solubility trapping, I mean, I mentioned that a little bit. That's where it mixes with the brine and the subsurface becomes a bicarbonate, and that's where it's stored over time. And then really what we're going to get to when we talk about the Columbia River basalt is mineral trapping. This is actually where it becomes a mineral rock phase, becomes a solid, and then it is really immobile. You can't make that flow again unless you substantially change the pressure, temperature, conditions of that rock. And so that's the special thing about working in the ultramafic rocks, the basalts that we have here in the Pacific Northwest. And basically that's where you have calcium, iron, and magnesium, what those rocks are rich in. Columbia River basalts, about 14% of that is iron. And that's total iron between ferric and ferrous iron. They have a content of magnesium about 4 to 5% of the rock. And then calcium is about 10%. So a significant amount of those elements within the rock, they react with the carbon dioxide and make precipitate these carbonate type minerals, essentially turn it into rock once it's in the space. Okay, on to, sorry I'm making you run, Connie.
It's
All right.
you,
Okay. We all need steps.
exactly.
All right. Okay, so where could it be stored? This is based on USGS information, US Geological Survey, sorry for the acronym. In a number of studies that have come out both in 2013 and 2018, some national assessments of carbon storage, trying to figure out where, the first place you have to start is where could we put this? Even if we wanted to do it, where would we put it? So the first thing is kind of these saline formations across the Midwest, the north shelf of Alaska, off into the Gulf Coast. Does anyone recognize what the correlation with these areas is? This is, yeah, this is, well, it's a traditional oil and gas production in the United States and in Canada, okay? Into the Gulf Coast, obviously we're all familiar with that, into the Alberta, Canadian basins there, and then the North Shore of Alaska. So these are traditional oil and gas plays, the marine type formations where those come from. And I'll point out, even into where Texas is there, the Permian Basin, I think we've all heard of that, West Texas, limestones there. Okay, we have offshore formations as well, and these also produce oil and gas there in the Gulf and East Coast of the United States and the North Shelf of Alaska. And then on the right, the basalt formations. And so these are really in the Pacific Northwest. It shows a little bit in Alabama and Georgia, but I think in the United States, we're really focused on the Columbia River basalt here in the Pacific Northwest. And it's one of the few areas in the Wallula Gap study that's been conducted there over the last decade or so has produced a lot of nice results, at least more understanding of what the system is doing if you inject CO2 into it. Okay, next slide. I'll go ahead.
Just quickly on the Wallula Gap,
Yep.
because that is right here.
Yep,
So
it is.
again, very unique.
50 miles that way.
Yeah,
Yep.
it's drive actually. And so it was we're actually just learning about the Wallula Gap thing. It happened in 2013 and
Yep.
it was put to the side for like a period of time for some reason, unknown reason. And now it's being picked back up by the Department of Energy and the Pacific Northwest National Laboratory has been doing some analysis on it. So because of their now picking up that data and looking at it again, that's why we started hearing about it again. Or even the first time from my experience. And so this is something that has already happened. They've already done it. And so now they're in. It's just relevant that it's right here. It's literally in the tribe's homeland.
Yeah, Wallula Gap is out on the Columbia River. Everyone's familiar with where that is, just south of Tri-Cities. Kind of on the border of Oregon and Washington. All right, so we talked about this last night. I went over the Columbia River basalt. I won't beat that in detail again, but that's the distribution of the Columbia River basalt in the Pacific Northwest on the left. That kind of orange polygon that covers the, not tri-state area, it actually goes a little bit in Nevada and even perhaps a little bit into California. So a really regional unit, that's about 160,000 square miles in its distribution there. I talked last night also about the flow sequences, and I'll show you a little bit about that in the next slides. But really, it's those kind of stacked sequences of lava flows. The target becomes a relatively small area in the pink area. So the characteristic of the Columbia River basalt is those pink areas that divide individual lava flows. So a flow came in, buried the landscape, sat there for a while. kind of has a broken top to it. The next lava flow comes in, buries the landscape, sits there for a while, and so forth. We build up this landscape. At the same time, though, you don't just build up a landscape higher and higher and higher. There are subsidence that's going on as that landscape sinks, basically at the crust of the earth and the mantle interface with all that overburden. Crust of the earth has to begin to sink into the mantle. And so we get this really deep basin, the Columbia Basin, where I mentioned last night, the depths of these lava flows have been drilled down to at least 14,000 feet that we know. They're at least that thick. So this is a very, very thick area of these lava flows. As you get areas east and south, there are areas of where they're fairly thick, several thousand feet, but they generally are kind of lapping out over older topography and didn't consistently make this really thick unit. They even go out offshore into the Pacific Ocean on the Astoria fan as well. So, but the basic characteristic is it has storage room, this open space. But if you imagine it, the little grains of sand that we showed under the microscope, in the basalt, they might be large angular blocks that have large spaces between them. So I mentioned last night, great for holding our groundwater. In this area, the Columbia River basalt is the region's largest aquifer system for sure. And these aquifers occur at multiple levels within the Columbia River basalt. And so that's largely what my studies for the last 20 or 25 years have been on, understanding how groundwater is distributed in these, and then how we can do detailed hydrologic modeling to really understand it. But now that modeling is becoming important for understanding this type of system as well. Yes,
Can I ask a
sure,
question?
absolutely.
Would you say it's a fair categorization? Space is for groundwater, and that's the space that we're talking about for this geologic injection, that it's kind of the same spaces I'm looking at, not necessarily all drinkable, but like all the way down.
It's not the same space because, for instance, what I mentioned in my first slide, we're looking at, and the poster mentions this, below potable water sources, but it's also greater than a kilometer, the depths that we're looking for. The deepest ag production well in Oregon, I mentioned a little bit last night, is in the center of the Grand Ronde Basin, and it's 4,400 feet. So, you know, that's about 1.5 kilometers, maybe a little bit more than that. So largely this exploration is going to go far deeper than any of the water sources that we use now. And you run into a variety of issues as you get deeper, because temperature of that water goes up. It may have its own mineralization that's gone on and contributed metals and things to the water. The water quality becomes in question as you go deeper. So I would say, no, not likely that we're sharing the same space, right?
But it's the same pore space.
It's the same concept and principle, but yes, the drinking water is not going to be displaced to hold this because they reside at 2 different vertical levels. Does that make sense, everyone?
Yes, thank you.
Okay, and so, and then just on the right, this rock is not, let's see, this is not Columbia River basalt. This is actually a sample from Iceland where they're doing injection like this. And so the basalt is the black, and that's a core, and the white is the carbonate.
The
Mineral that's actually developed. So that is a CO2 gas that's been injected, has turned to a solid phase, filling those pores. And what the pores are called vesicles. When the lava flow actually cooled at the surface, it's a liquid. So if you've ever seen a video of that, as it cools, basically the reason that it cools is because gases start dissolving out of the liquid. So the gases in it keep it hot, help it to maintain a very low viscosity so it flows. But as it gets to the surface, all those bubbles are migrating out into the atmosphere. So that would be CO2, because volcanic rocks are a major contributor of carbon dioxide and other greenhouse gases. Yeah. So, but as that gas bubble leaves one at a time, lava flow begins to increase in viscosity, lower in temperature, and become a solid, and it stops. But when it stops, those are the remnant gas bubbles where that bubble went out of it, and you're left with that. And so then that is now the storage space to put carbon dioxide back in. Yeah.
Yeah.
Pretty cool, huh?
Yeah.
And so then that's a scanning electron microscope image on the left of a carbonate mineral. Yes, please. Yeah, moving on. Okay, so just I wanted to introduce a little bit. What's that?
Yeah.
So this is actually a map, geologic map. So I explained a little bit of it last night, what I do as part of my research. The multicolors in there are representative of all these different Columbia River basalt flows at the surface. Both maps are of the exact same area. The one on the left actually shows all the soil cover that people farm in the Athena area. And I should point out in the map on the very left side center, that's the city of Athena. And so the lower part of the map is the northern part of the reservation here. Okay, and it would be down Wild Horse Creek, down in there. All right, so the one on the left has all the soil cover over the top. The one on the right, we've actually made it so it takes all the soil off and just shows you the underlying geology in there. So these are the maps that we produce. On the left is actually a listing of all the flow units in the Columbia River basalt at a what we call a member scale. So within those members, there might be hundreds of different individual flows, but I wanted to give you an idea. Each of these flows has been determined throughout the Pacific Northwest by making maps like this, analyzing the geochemistry of them, and then putting it together from Lewiston to Pendleton to Steens Mountain to the coast. And we've come up with this really detailed stratigraphy, and there's numbers up the middle of it that are ages. We've actually dated these rocks so we know what age and how they fit together. So just for example, with the chemistry, one of the flows called the Pomona that erupted in the Lewiston Basin at 12 million years ago, we can trace it by chemistry throughout the Columbia River Gorge and to Astoria. The analyses are the same from west to east backward erupted. So, but we've been able to create this chart of the order of lava flow. So I wanted to add that from our discussion last night. Yes.
Just to clarify, is this the updated effort that you're doing? I mean, at this level of geologic maps, like at this scale?
The map for the Columbia River Gorge will look like this.
Okay, and that's what you're working on now?
With the US Geological Survey, and we use LiDAR as our base map.
Okay,
For doing this, yes.
okay.
Yep. And so that is, yes, and it's not represented on there, but most of those places I've either driven or walked and collected samples on. And Katie Ely here from the reservation helped us with the southern part there.
Okay, so currently, is there something that you could look at to see the different types of basalt along?
Yeah, we have a web map on our website. So the entire geology of Oregon, we have a map for, and there's a web map. It's
Your individual, your agency's site?
Yes.
Okay.
We have, if you go there and you look at publications, it'll say online data or GIS data, and we have a number of web maps that will tell you about hazards, landslide, tsunami,
Yeah.
and what you're looking for is geologic maps.
Okay.
And it will have a web viewer that you can go in and look at the geology. Now, what I'll say, the map I referred to that we're making in that area, it will need to be published first, and then will be added to that as we add new information to it all the time. So,
Okay.
And it's the database behind it is called OGDC, or the Oregon Geologic Data Compilation. So if you have GIS folks, they can download it and then use the data in ArcGIS. Good question, though.
Thank you.
Okay, let's go to the next slide. Okay, so there's a small scale map, and at the bottom, there's this representation of a cross section. So this point, so you can see. This line here at the city of Athena, down here to Wild Horse Creek, that's called a cross section line, and the bottom is called a cross section. So if you took that map, turned it on its side, and you sliced it down right across that line, and then opened it up so you could see what the Earth looks like, that would be that representation there at the bottom. And so these are major faults that break the Earth's surface, and these are, individual colors are the lava flows in space. And so a natural question would be, well, how do you know the order of those that go down, 2,000 feet or so? And largely that's because at the city of Athena, we have a deep water well that goes down nearly 1,500 feet, and we've collected geochemistry on intervals of that and have been able to tie it to what we know at the surface, create this third dimension representation. So this is in order to understand carbon sequestration in the Pacific Northwest and its potential and feasibility. This is the type of thing that we have to know as a baseline of what the stratigraphy is, what unit we'd get into. For instance, in the Wallula project, they got into what's called the Ortley and Indian Field basalt. So in our stratigraphy here around Wild Horse, it would be down in this near the lower part of the section. Groundwater production in Athena is almost exclusively up in this upper part of the section. So just to give you an idea of how that's kind of divided around. I guess I'll stop right there. Any questions about this, what I'm showing? Okay. All right, next slide. We're almost done. Okay. I showed the point sources last night for industrial carbon dioxide in Oregon, and the lower left kind of breaks down by different entity, what their production looks like, power plants, the overwhelming kind of emissions there. I just wanted to introduce direct air capture because this is a project that is actually starting to go on in Oregon, where you take air out of industrial sources, you extract the carbon dioxide and then you put it back to some other purpose, like decaffeinating coffee beans or something like that. It's one of the ways it's being used. Or it's stored in the ground. So, I mean, this mentions some of the ways that applications that it might be reused and take it out of the system, or goes directly into underground storage. I didn't mention this last night, but it is something that we're not involved in directly, but there is a project going on. Okay, go ahead.
Yeah, thank you for bringing up the direct air capture. It is something that we have here mostly because it's not to the extent that at least I know of. And it seems fairly energy intense to do this. So that was something that I kind of wanted. What is the energy of this process? The injection, I know that you're not involved with air capture, but the injection part of it. You had mentioned it's a supercritical fluid. Thank you for that word. I've been looking for that word. I'm like, it's not a gas, it's not a fluid, what is it? And so from my understanding, again, talking to PNN, stored at a very cold temperature, but then it has to be heated up to be injected. That seems like that's a very energy intensive process. And so what is kind of the trade-off? Are we going to be burning coal to be putting carbon back into the ground?
I'm not in direct air capture. I don't know the answer to that, but let me, the way I will answer it is that there's a feasibility study that's going on that we basically wrote a letter of support for the organization, a private organization, to look at.
They got it.
In Hermiston.
Yeah.
And I think those answers will come out of that study. That's about all I can say about that because we're not involved and it's a, private research.
So Wyoming.
Yeah. Okay. So anyway, I think the answer that you're looking for is going to come out of that study. That's where I will step out of my expertise and say, I just don't know that answer. Yeah, but it's a really great question about a lot of these. I mean, that's kind of what's been on the top of my head. Listen to everyone all day is what is the energy trade-off for doing a lot of this stuff. Yeah. Right. Okay. Okay. And then I thought about last night after I got home of some of the things we talked about are, benefits, but also the negatives, because I don't think I touched on that. And there were some questions about that. So that's part was really helpful. So I mentioned last night, this is the feasibility studies that people are going to do now and that we're going to be involved in really are looking at, how could this be used to limit negative effects of carbon going into the atmosphere? It's one piece of a possible portfolio to investigate. That's where we're at right now as the state of Oregon. And really, I think the part I put in there, until these other carbon-free energy sources become available. And that's where we get into our connected studies where we're looking at what type of critical minerals are we going to need to produce domestically in Oregon, because I mentioned it will come to Oregon or has come to Oregon, and across the nation. You know, how are we going to do that in a environmentally friendly, green way, and considering the things that you mentioned last night about tribal relations and all the other impacted community. There you go. That's a good term for it. So basically, that's where we see carbon sequestration as part of a portfolio to get us to this part of a carbon-free energy sources. Okay. And so I just put in here one of the USGS estimates from a 2013 study where they looked at nationally carbon sequestration potential. And so in onshore areas and state waters, that's kind of the areas I showed you in those maps of the United States. There's about 3,000 billion or gigatons of subsurface capacity in the US. That's a very abstract number. What does that mean? Basically, it's about 500 times more than, in this study was 2015, so I put 2011, than what annual energy emissions are. So, and based on USGS findings, this is something that could get us through several decades. It's not a long-term thing. Remember I talked about last night, like there's a infinite amount or a finite amount of space you can fill up with this, and then that solution goes away. But the prediction based on this, at least in the US, would be several decades of.
Well, I just wanted to tour the PNL last, so they had kind of a mile radius around the little area that they were looking at. And they gave the estimate of it could store roughly 4 years of the nation's carbon emissions.
Right. That doesn't seem like much. It's something. But
It's a stopgap measure.
yeah, that's exactly right. So yeah, that's a good way to put it. Okay, and then negative effects. So obviously, you do have the potential. The Earth is a dynamic place. It's not static. Many of these areas are seismically active, including potentially around here. We have historic earthquakes that melt free water. The Wallula Fault Zone heading into Wallula Gap is one of the more active fault zones in the Pacific Northwest. And we know that it has, in the time period of the Holocene, which is the last 10,000 years, we know that there are Holocene ruptures of these faults along the Wallula Fault Zone. So very active geologic environment in this part of the Pacific Northwest, but also including Western Oregon. We've all heard about the Cascadia subduction zone and its potential for mega quakes there. So some of the Western basins that would be targets for this there are indirectly seismically hazardous zones. So as geologic formations could change and break, you could have gas leakages. You could have, if they're sharing the same space, CO2 could get in, seep into underground drinking water. And then those reactions could release metals from the rocks that contaminate the groundwater. Certainly potential for that. For the CO2, if it weren't stored properly and there was some kind of vertical conduit that got it back to the surface, you could have a revolving door cycle to get it back into the atmosphere, and then you wasted a lot of, like you say, energy and resources to accomplish this. But I will say about those first three is kind of in the Columbia River basalt. That's the point of looking at a basalt formation, is putting it down, making it a solid. When you make it a solid, then those top three basically are non-starters and are not really concerned. So that's kind of the benefit of going this way.
One of the reasons our region is very.
That's correct. That's correct. It's trying to get away from a lot of these risks. Reducing risk. Nothing is without risk, but we're looking at reducing risk. And then the very good question that came last night was about induced seismicity or potential to create earthquakes. And this has been demonstrated from fracking and that kind of operations in Oklahoma, Louisiana, where that's induced earthquakes, in the Colorado basins, which were mentioned last night. So anytime you put a fluid under pressure into the subsurface, it has the potential to shatter rock and change the dynamics of things. There's also interesting things that happen is when you create this reservoir, part of it is you have, in that cross section I showed these vertical faults, those are kind of your bounding structures on the 3D area. And so you could mineralize into those and have carbonates go up into these fault zones and actually induce faulting or structural offset, could basically grease the skids. Okay, that could happen too. You induce offset on that fault where you didn't intend it. So a big part of this is really having studies that understand the constraints of the reservoir, understanding how the supercritical fluid is going to move through this, how long it's going to take to crystallize. That's what's come out of Wallula Gap, is basically, they put it in there, re-drilled areas around it over several years and see how it's crystallizing, what are the chemical changes that are going on, and trying to assess how is this fluid migrating. And then of course, in our Pacific Northwest seismic network, trying to see, is there induced seismicity? Are there micro fracturing or quakes that are going on? In those drill cores, are we seeing micro fracturing going on in the reservoir? So that's part of the gap study and what you look at over time. And then developing what are the pressure management techniques. You might have to babysit this thing forever. It gets into how much resources does it take to do this. Yeah, you can't inject it and leave it. I mean, that's even true with oil and gas, That's a very dangerous proposition when you're putting a hole down 15,000 feet. The pressure conditions, I mean, there's plenty of examples of explosive wells and things like that. So it's a dangerous proposition, or can be. As far as we know so far, with the amount of these types of operations that have been done, this is a rare occurrence of induced seismicity. But like lots of scientific things, longer studies are going to be needed, more detailed studies. So, all right, I think I've talked long enough. Oh, I just want to make you aware. So in neighboring states, Washington Geological Survey, they've put 4 people employed in their survey to look at this, assess sites, and they have this very strong relationship with PNNL. The California survey to the south, they have 3 major projects going on, and 3 people have been advertised to fill those positions at the end of the summer. Nevada's got some involvement in carbon sequestration, and Idaho is looking more at these natural climate solutions. And so Oregon, basically right here, we're having information gathering to see where we go with a program of study like this.
And like I had mentioned, University of Wyoming.
Right, it's Rocky Mountain. Yeah. All right, that's it.
I just wanted to thank you for providing this information to us. Like we're really catching up on this. And I know that you have said that your department is catching up on this too, but we're starting from really the basement and learning about all of this. And so not everyone would come to our longhouse and present. I actually just really wanted to thank you for coming out here, taking the time to talk with our community about this. Does anyone have questions?
I apologize if you mentioned this. I know you said you're learning about the length of time it takes to mineralize from this study. And that's part of doing more studies. But like when you showed that one example, core in Iceland, or even just what they've learned from the study here, like what are you talking about? Like years, months, like how long till it starts to fill in the spaces?
Less than 2 years.
Okay.
Yeah, so in Wallula Gap, they have some initial, well, not some, a lot of initial cores that go down. And where you see rock that basically be barren of this type of mineralization. So they injected CO2 into that at a certain depth. And then basically after certain years, a year, 2 years, have re-drilled through those same sections and looked at, okay, what is the mineralization now? And so basically then you start to see cores come up like this. And they're not just naturally appearing like that, because they're also putting isotopic tracers in here. So they know it's not naturally occurring carbonates. It actually relates to what they put in. So it has basically a tag that's been put in it so we can identify it again. But basically they started to see this show up after 1 to 2 years.
Very rapid. Understanding at the end. Their estimate was.
Yeah, that comes out of the latest 2018 USGS report on carbon or geologic carbon sequestration. That's the information I have.
Again, another reason our area mineralize and become a solid, it does it very rapidly.
Yep. Yep.
Yeah, I think that's great. Thank you. Great, before we go to our last two, we just want to roll through. Are you guys feeling? Let's roll through, Steven says.